So as we start work on the Module 3 solution, the first step is to draw a diagram. And what we're going to do is just post this one assignment without a due date. But ideally, it would be great if you could get this done before 11:59 p.m. today. Essentially, you're going to want to design a complex logic gate using 4 or more logic gates, and 3 of them must be different. So in the last module, you had your basic digital component you built from more than one type of logic gate. Now we're going to take it up a level. We want at least 4 logic gates, and 3 of them need to be different. Now, you must submit a Word document with the proper name that includes the following artifacts. The implementation view is actually this assignment. Does everybody understand that? So if you draw the diagram of a complex logic gate that has at least 4 or more logic gates, and 3 of them are different, when you draw that diagram, if you draw it in a certain manner, it shows the inside components of your digital creation. Yes? So you're creating a digital component, and what you're doing is mixing it up. And when you mix that up, essentially, you need a foundation from which to work. That's what this assignment is about. So the thing that I would offer to you at this point is 3 of the logic gates must be different. I do not want you to consider a NOR to be 2 different logic gates. A NOR is built from 2 different logic gates, but we have introduced NORs, NANDs, XORs, XNORs, MUX, DMUX. Each of those are individual logic gates. So when I say 3 of the logic gates must be different, one thing that you should not do is say, well, I have a NAND, and a NAND is technically an AND and a NOT. Okay? Does everybody understand what I'm saying?
Yeah.
Yeah. So you take the same basic diagram from module 2, and instead of using an AND, you throw a NAND in there and you say, okay, I'm done, because a NAND is actually a NOT and an AND. Nope. At this point, we have described the behavior of a NOR, also a NAND, as a distinctly unique and separate logic gate, right? So it's more sophisticated, it's more elegant, it has some secret sauce in the mix, so that we get a different output than we would with an AND or an OR. And so that needs to be treated like one logic gate. An XOR could be treated like multiple logic gates, except that, well, depending on how you build the XOR, we've already explained that an XOR can be built with 3 logic gates, or it can be built with 5, right? And we don't want people to get confused about the internals of each of the separate logic gates as part of this requirement. No, we want you to come up with a diagram where you have 4 or more logic gates. And you don't need a lot, right? But you also, so there's kind of a walk on a tightrope going on here. You can do more logic gates, but as you keep adding 4, 5, 6, 7, I know that some of you felt inspired and ambitious, and in module 2 you gave us more than what we were asking for, and that was a much higher level of challenge, and that was significant. And I think that's great. If you go more than 4, you don't want to paint yourself into a corner. So even though it says 4 or more, it's perfectly normal if we have 2 of the same kind and 2 other different ones. And so you have 4 total and 3, and you meet the basic requirement here, okay? So the other thing that I want you to understand, in our Monday session, we talked about the additional features in the HDL simulation environment and how the HDL simulator provides additional readouts of what's going on with the internal pins. So if you can stick with the convention that we've seen in class recently, where if you have a NOT that leads into another logic gate, instead of calling the output W1, you could call the output NOT A or NOT B. Does everyone know what I'm talking about?
Yeah.
Okay. And so you can kind of remain consistent with the textbook conventions, right? So now that you know that it's okay to label a wire for output a little more intentionally, that can actually provide extra definition that becomes helpful if you're troubleshooting a misfire. So at this level, the more complex you become, the more opportunities there are for something not to work. And in simple terms, if everything's just W1, W2, W3, WX, all the way, you know, W16, W17, it's harder to pin down misfires. But the example that the author used with NOT A was a great example of how outputs can be labeled in a simple but elegant, more descriptive manner, right? And I want to encourage you to consider that aspect of the assignment, right? Just as your previous salute, any questions so far? Any questions so far? So this assignment is worth 1 point, and I need you to do it as soon as possible. And I'll tell you what, let's just say we'll do it by the start of class this Friday. How does that sound? I didn't put a date. I said maybe everybody could get it done by midnight. I don't want to stress you. Can everyone agree that we would have this finished by no later than the 14th at 10 a.m.? Do we have
Okay.
Yeah.
do we have an accord? Is everybody cool with that?
Yes.
Yes.
Okay, now can we also agree that by Friday, 10 a.m., you'll go ahead and like email me your diagram or post your diagram, and I'm going to change this right now so that you can submit more than once, right? So I'm going to change this so you can submit a couple of times. Yeah. And so if you go ahead, what I want you to do is upload your initial diagram and then send me an email that says, hey, I have a diagram. If you could have a quick look at it, let me have a look at it. So if there's any quick fixes, any quick adjustments to the diagram, that can also be done before 10 a.m. Friday. Is that also a matter we can agree on?
Yeah.
Okay, great. Great. Excellent. So I'm going to go ahead right now in front of you, and I'm just going to go ahead and post the rest of this assignment now, and this is due 10 a.m. Friday. No, that's not right. Next Wednesday would be the 19th. So I don't know how that got in there. 19 Wednesday. Yeah, all right. So give me 1 second here and we'll have this posted, right? As a reference. I may attach other references or rubrics, but basically, there we go. Any questions so far?
Could we use our old diagram and just add to it?
That's a great question. And I am so very glad that you did that. Or and asked that question. So yes, the short answer is yes. Now, you're going to want to read all of this. It says it must include an XOR, an XNOR, or a MUX, right? So you have to have 3, but in addition, let's add an XOR or an XNOR in the mix. So one of those 3 needs to be an XOR or an XNOR or a MUX. So 5 requirements. The diagram, this means the diagram is actually worth twice as much, right? So you get credit for it when you submit for 3.0, and then you get another point when you include it here. The truth table, the canonical expressions, the HDL file with a valid logic statement, and then true and false case that matches output options shown in the truth table. So what does that last requirement mean? You enter inputs that will generate a 0 correctly. You capture the screen. You enter inputs that would result in a true. Then you capture the screen. So you have false and true, right? Outputs. And it shows that if we have this row of the truth table, here it is on the screen, the chip works for this false case. Here it is, we enter the inputs for a true case. Here it is on the screen, the chip works for a true case. So you want both cases, true and false, right? True and false. Does anyone have any questions about what that means? So there has to be a single Word document, but then there's also a separate HDL file. So you're going to give me the HDL file, and I'm going to take your HDL file and I'm going to run it. I'm actually going to load it on my screen and see if it works. So apart from the artifacts that you paste into the Word document for each of those 5 steps, you include the HDL file along with that. So it'll have a .hdl extension, which shouldn't be any problem uploading in there. Any questions about where we are so far? Okay. This is a challenge assignment. This is going to be assignment 3.1. And what you see here on screen, I'll just go ahead and open up a new paint window and let's. I'm gonna post this in the 3.1 challenge assignment. And one of the things that we want to do is become comfortable with working a diagram. So part of the competencies we want you to develop in module 3, you created your own in module 2, and we've walked through some things together. And now in module 3, if you see a diagram like this, I want you to be able to tell me some things about this diagram. And then I want you to be able to resolve the output for this diagram. And this looks busy. Can we all agree that this diagram looks, in a word, busy?
Yeah.
Yes.
Yeah.
Yes.
Yeah, it does. Now, one thing I like about this diagram is that it doesn't label each of the basic logic gates. So it gives you an opportunity to show or demonstrate, okay, first of all, I know what each of these are based on the shape. That's one plus. The other thing that I like about it is that they only use 2 different types of logic gates. And this diagram begins to give you a sense for how creative and complex just a few combinations can get, right? Here's a third thing that's very useful about this diagram. Based on the way the drawing is made, do you have any problems identifying where the inputs split or fork?
No.
Okay. So if my input for B is 1, let's walk through this. Where does 1 present? In which logic gates does that 1 show up first?
The and.
All right, which and are we talking about?
The one on the bottom.
It goes down here.
Yeah.
Okay, so the 1 flows and then it splits. And then that little hump says, okay, that wire crosses over the C, right? So that's what that convention means. Everybody knows this, right?
Yeah.
These wires are laid over on each other, but they're not connected. These wires don't lay over each other and they are connected, right? So it comes down into here, and we're going to call this the bottom of, let's see, if we start from the left and go to the right and work down, this could be like the first and, the second and the third and. It all depends on how you want to do this, but you can have your own way of keeping the different ands separately. So this is an and. What are we dealing with here? Anyone? Or, absolutely, or. And if we had a double line that's curved back here, what will we be dealing with?
No. Wait, no.
No, it would be a shape like this with an and. It has to be some kind of or, but if it has a double, XOR is correct. XOR is correct. So if this curve had another double curve, you'd know that this was an XOR, right? So that's where the study guide comes in handy. But okay, so the B presents down here. That is correct. There are 2 other places where the B presents. Can anyone walk me through the other 2 places where if I had a true for B, it would be an input in 2 other places?
It would go to the or and.
Which or? This
The or in the middle.
This or?
The or in the middle and the
middle.
and on top.
So it would go into the or here, and then it would go to the and on top. So the 1 would flow, it would split. A 1 would continue here. At the same time, a 1 would flow down here. It would hit here and flow into here, and then it would flow into here, right? Oh, I also want you to know that these are big A's. And then what we could do, since it's an implementation diagram, is we could have like a little a little b, And then we could have like a little a and a little b, because these are big A's and big B's, right? So this is the inputs for the whole thing, and Q represents the output for the whole thing. Sometimes you'll see output represented as Q. So everybody remember that. Sometimes out is represented in a diagram as Q. Question. Does this meet the requirement of your solution?
No, because
No.
we do that
No.
so
Everyone is correct in saying no. What is it missing?
Or
Another type of logic gate.
It has to have another type of logic gate, and it has to include at least an XOR, an XNOR, or a MUX, right? So you could make this a NAND, and then it would have 3 different kinds of logic gates. If I made this a NAND, would it meet the requirements of the solution?
no,
No.
because you don't want a NAND, you want a mute XOR and
Right.
what the other one, I forget what it was.
Right. You could have a NAND, but it wouldn't satisfy the additional requirement of having an XOR and XNOR or, all right, I'm glad we got that clarified. Okay. Now, here's what I'm going to do. I'm going to post this as a challenge assignment. And what's going to happen is that you're going to have a chance to resolve this. Okay. And this is something that you can complete between now and next Wednesday. And how many original rows are we going to have in our truth table based on this diagram?
Can you repeat what you said again?
I was waiting for it, and then there were crickets, and I'm supposed to wait 5, 6, 7 seconds for complex questions. My question is, we have 3 inputs overall for this diagram. So the initial truth table, before it's developed, must have at least how many rows?
8.
It must have 8. That's correct. 2 cubed is 8. So it has, to start with, 8 rows. And to start with, it has how many columns? The basic truth table.
Like 4?
No.
Yes, 3 inputs and 1 output. It has 4 columns to start with. But what I'm going to tell you is that as you consider the results of the truth table inputs, you're going to get different results in each of these cases. So you're going to add more columns. You're not going to increase the number of rows, but you're going to have to differentiate what happens here, what happens here, what happens here. True or false, these 2 logic gates receive input from A, B, and C, big A, big B, and big C directly.
true.
Okay, we have a student who has said this logic gate and this logic gate receive inputs from big A, big B, and big C directly. Does anyone agree with that? Well, nobody's spoken up, so I'm going to assume that they don't. I'm glad you answered. That's not the case though. Big A, big B, and big C, if you trace each of the inputs for big A, big B, and big C with the basic truth table, A and B hit this one. Which inputs hit this one?
B and C.
B and C hit this one, yes. Which inputs hit this one?
C and B.
Say again?
C and B.
C and B, yeah. C comes into the top, but then B comes into the bottom. So the fact of the matter is that the order is reversed, but it's still it's B and C for this one and B and C for this one. So what we have are initial results where A and B is applied to this and, B and C is applied to this or, and B and C is applied to this and. And we have initial outputs here, here, and here. And each of those in turn are fed into other logic gates. So these two do not receive directly from big A, big B, and big C until the intermediate logic gates are resolved. Once those intermediate logic gates are resolved, the output from the top, and we could call this top and we could call this bottom and we could call this middle and, right? It all depends on what convention, labeling convention you would like to use. But you're going to have to label this, and you're going to have output from the top and, the middle or, and the bottom and. Once you have those outputs, you can feed the outputs of this middle or and the bottom and into the middle and. Now, when I say top, bottom, and middle, I'm just saying this is kind of, if you slid it over here, it'd be like in between the top and bottom. Does everybody see what I'm talking about there?
Yeah.
And in terms of position, this is like a top or, and this is like a middle or. That might be one way to describe it. You might simply just say and one, and two, and then when and one and and two are finished, you can also use subscripts. Everybody here familiar with chemistry? You've heard the term H2O?
Yeah.
Yeah.
Okay, so you can use subscripts and have and sub one. If we were completely accurate about how we do things for hardware, we'd say and sub zero. Because the first component in any digital configuration, right, is always the number it receives is zero. Like disk zero, USB zero, network card zero, right, NIC or network Ethernet zero, that kind of thing. So that's what we're dealing with. So you could say and sub zero, you could say and sub one, and then the outputs from and sub zero and sub one, along with or sub zero, right? Those results are inserted into additional columns on the table, right? So we insert additional columns. So we have the results of and sub zero when A and B is inputted in there, and then B and C with this or, and B and C with this and. Then we have three additional columns, and then we have to, in order to calculate this one, I have to get the result of this first, because until these two feed into this one, does everybody see what I'm talking about?
Yeah.
The output of these two have to be fed into here first in order to get output before I can resolve this one. So even though I have output at the top that's ready to be fed direct, okay, so the next step is like, okay, right from this and to the other or. I can go straight in. I still don't have this value right here until I'm finished business here. So I have the column, I have the output and the column for this, but I have to have another column for these two initial results that I combine for this one. I'm going to go ahead and put this recording out along with the challenge assignment for 3.1. And what I'd like you to do is to start working on this first set of columns to resolve before our class on Friday. Now that's in addition to getting a drawing, right? So what are the two things that are due before class? And what have we done today? Well, we've reviewed the assignments. The first step is to have the drawing done before class. The drawing has to be submitted and meet all of the requirements for the solution. So even though the 3.0 assignment is plainly stated, you need to complete it so that it meets the requirements of the solution, right? And that has to be done by Friday. What else could you do by Friday? You could have your basic table set up with the results for these first three combinations ready by Friday so that we can review what that looks like by Friday. How do you eat an elephant? One bite at a time, right? Once we have your drawings on Friday, we can start the process to develop the truth tables for your drawings on Friday. And we can take this the rest of the way across the finish line. So by the end of the week, you could have a completed solution for this, and you could have most of what you need to build your HDL for your solution, okay? Be sure you take some quality time to finish studying the Module 3 study guide. And over the weekend, I will be putting out the assessment for Module 3 so that by the early part of next week, we will have the assessment for Module 3 completed. Any questions before we stop sharing and stop recording?